Dear students, up till now we have studied the synchronous counter and the ripple counter. We have even seen the controlled ripple counter and controlled synchronous counter and then ring counter. Now we move on to another counter that is known as the mod 10 counter, or it is also known as decade counter, or it is also known as divide by 10 circuit or counter. So you can see the circuit. In this circuit we are using 4 JK flip-flops, and some special circuit arrangement is made such that the count should not exceed 1001. It means it can count up to 10 pulses. After that it will get reset. So how it works, let us see. The modulus of a counter is the number of output states it has. A 4-bit ripple counter has modulus of 16 because it has 4-bit ripple counter, so 2 raised to 4 is 16. So it has 16 distinct state numbered from 0000 to 1111, and by changing its design we can produce a counter with any desired modulus like mod 10, mod 9, mod 8. So now we are going to study the decade counter or mod 10 counter. So the diagram shows a way to build modulus 10 counter or decade counter. This circuit counts from 0000 to 1001. On the 10th clock pulse, the counter generates its own clear signal and then count jumps back to 0000. The output count sequence is like this. So here is the count sequence with the clock pulse. Initially clock pulse is 0 and initial count is 0. With clock pulse 1, 0001 is the count. Then with 2, like this, up to 9 it is 1001. So right from 0 to 9 the total number of states is 10 and the last count is 1001. As it reaches to 1001, after 9th clock pulse it gets reset. Why it gets reset we will see in the circuit. Here we are drawn the state diagram of the decade counter. You can see how it is going. See, 0 to 1 state 1, 1 to state 2, then 2 to 3, 3 to 4, 5, then 6, 7, 8, and after 9th again it moves on to previous one, 0, the first state. The circuit skips the states. You can see circuit skips the states from 10 to 15, that is 1010 to 1111. Even it has 4 JK flip-flop, still it is skipping the states from 10 to 15. The counting sequence we have seen already, and you can see in the state diagram also how the counting is occurring. So 0 to 9 and then 9 to again 0. Now why does the counter skips the state from 10 to 15? Because of the AND gate. Now let us have a look at the circuit. Because of the AND gate, the counter can be reset by a low CLR. This is low CLR or a lower value of Y. Initially CLR goes low to produce Q is equal to 0 0 0 0. When CLR bar returns to high, the counter is ready for an action. The output of the NAND gate is as we have written, Y is equal to Q3 Q1 bar. This output is high for the first 9 states, that is from 0 0 0 0 to 1 0 0 1. And nothing unusual happens when the circuit is counting from 0 to 9. On the 10th clock pulse, however, the Q is equal to 1010. So when Q becomes 1010, then Q3 and Q1 are high. Almost immediately Y goes low as Q3 and Q1 becomes high. 1.1, 1 and 1, its complement is 0, so it becomes 0. So Y goes low, forcing the counter to reset to 0 0 0 0. Y then goes high and the counter is ready to start again. Since it takes 10 clock pulses to reset the counter, the output frequency of Q3 flip-flop is 1/10 of the clock frequency. This is why a mod 10 circuit is also known as a divide by 10 circuit or divide by 10 counter, and it is also known as decade counter because it counts from 0 to 9. It is a natural choice in BCD application like frequency counters, digital voltmeters and electronic wristwatches. So to get any other modulus, we can use the same basic idea. For example, if you want to design a mod 12 counter, you can drive the NAND gate with Q3 and Q2 instead of Q3 and Q1. Then the circuit counts from 0, 0, 0, 0 to 1, 0, 1, 1, which is from 0 to 11, that is 12. So on the next clock pulse, Q3 and Q2 are high, which clears the counter. Then a mod 12 counter can be designed in this way. My question for you is to design a mod 12 counter and to design a mod 8 counter. For any doubt, you can ask the question in the group.